will discuss today several real enumerative problems. And as you definitely know, problems in the real enumerative geometry are often even formulated differently comparing to the problems in complex enumerative geometry because of lack of invariance in the real setting. Since the field of real numbers is not algebraically closed, so there is no invariance for free in the real setting. But it turns out that so if we try, for example, to enumerate curves, algebraic curves in an algebraic surface passing through certain points, so for example, we can, for this talk, decide that we discuss algebraic curves in P2. So we fix some number of points in P2, and we try to trace through these points curves of given degree and given genus. So if we work over the complex numbers, then the answer is, well, the answer does not depend on the choice of points, provided that the number of points is fixed and the points are in general position. But it's no more true over the real numbers. So I will discuss today several problems of this type over the reals. But the main observation, so it's the observation of the result due to Jean-Philippe Changer. So Jean-Philippe Changer noticed more than 20 years ago that if one enumerates real curves with appropriate signs, then in certain situations, quite rare, but still in certain situations, one gets an invariant enumerating real curves. And so let me recall you the first instance of this Villachange theorem, and then we'll discuss certain Villachange type invariants. So my main purpose for today will be to describe some new situations where this Villachange type invariance, where the signed enumeration of real curves provides an invariant. So let's first consider the following enumerative problems, very standard one. So we fix 3D minus 1 points in general position in the projective plane, and I will be interested in real enumerative problems. So we are in P2 of R, and I'd like to look at real rational curves of degree D, which pass through those points. So if we would be in the complex situation, if we would look at, well, as you prefer, either you can replace R by C here, or you can keep this setting, but look at not just real rational curves, but complex rational curves of degree D passing through my points. So just let's fix it now. So for me, a real curve is a real curve, for example, in P2. It's a complex curve in P2, which is globally invariant under the evolution of complex conjugation. So even in this situation, when I fixed points in the real projective plane, I can look at complex rational curves of degree D passing through my points, but now I'm interested in real ones. So if you enumerate complex rational curves of degree D which pass through my points, then the result does not depend on the choice of points, provided the points are in general position. And the number of the recurse, well, this number has many names. This number coincides with the genus 0 ground fit invariant of P2. These numbers are called Kontsevich numbers sometimes because Maxim Kontsevich proved the recursive relation for these numbers. So over the complex, we can speak about numbers and we can study these numbers. But over the real situation is more complicated because the number of points in this collection in general does depend on the choice of points, even provided that the points are in general position. So let's just look at very simple examples. So contrary to what I said, if D is 1, so if we are enumerating lines through 2 points in general position, then of course the answer is always 1 independently on the base field, because our problem is linear. It's still the case if D is equal to 2, the answer is still 1 for 5 points in general position in P2, one can always trace only one conic. But if D is 3, so starting from the case of cubics, there are several possibilities for an answer in our enumerative problem. And over the reals, as it was proved by Vyacheslav Kharlamov something like 40 years ago, there are 3 possibilities. It can happen that there are 8 rational cubics through 8 points in general position in IP2. It can happen that the number of this real rational cubics is 10, and it can happen that this number is 12. By the way, 12 is the number of complex rational cubics pattern. So it's, of course, the number of real solutions to our enumerative problem cannot be greater, cannot be bigger than the number of complex solutions, right? But it can be smaller. What is surprising here that the answer cannot be smaller than 8. Hope it's not a surprise for you that all these numbers, provided that 12 is even, it's not a surprise that all answers are even, just because if we are interested in the number of real solutions, so we can look at the number of complex solutions, and the number of real solutions, of course, has the same parity as the number of complex solutions, because non-real solutions, since our points are real, so the number of non-real solution is definitely even. Any non-real solution comes together with the complex conjugated one. But what is surprising is, for example, 6 cannot be realized in this. Well, so now let's try to get an invariant. Let's try to enumerate these real rational curves in a different way. Yes?
In case of D equals 3, no 6 points lie on a conic either, right?
No. So it's always the same problem. This expression general positions. It's never clear what does it mean. But of course, it's a general position. So no 3 points on a line, no 6 points on a coin. So it's an appropriate open dense subset in the space of configuration of points. Other questions? Yes.
Half the points, so is it clear which one can you effectively say?
Well, it depends. What do you mean effectively? So no, it's tricky. So if you have a concrete collection of points, you can try to figure out what is the answer, but it's not. So that I don't know any immediate answer to this problem. So all the 3 values are realizable. So I know how to construct configurations of points. Sorry?
They connected?
These regions, I think no. I think no. Yeah.
And if the points, the conditions are you allow them to come in conflict pairs?
Yeah, so it's a very good question. So in fact, what I will describe is a very particular case of a much more general statement proved by Jean of Ficharget. So I will describe this Ficharget invariance in the situation when all points are real, but you're completely right. One can consider real configurations of points, meaning that some points can be real and we can have some pairs of conjugated points. In this case, so this case is also covered by Ficharget theorem. So once again, you get an invariant if you consider the signed enumeration of these curves. But the value of this invariant depends on the number of real points in your configuration. So let's try to count these curves in a signed way. So now I'd like to associate a sign to each of the curves in our collection. And I'd like to do it in such a way that the result would not depend on the choice of points. Of course, points should be in general position. And so there is a rule of science called Ficharget science. So once again, to each curve in this collection, I'd like to associate a sign, plus or minus. So first of all, since my points are in general position, it's not very difficult to show that all curves in this collection are nodal. So be careful, I don't state that all rational curves in P2 are nodal, but I claim that if my choice of points is sufficiently generic, if points are in general position, then all the solutions to our enumerative problem are nodal, meaning that the only possible singular points are non-degenerate double points, transversal intersection of two branches of the curve. And for this is, if you prefer, the complex statement. So it's true, of course, not just for real rational curves, but it's true for all complex solutions to our real enumerative of our enumerative problem. So we have a nodal curve. And real nodal curve has some number of nodes of non-degenerate double points. And each point can be of one of three possible types. The first type is like this. So this is called hyperbolic node. Like this means that this point is a point of transversal intersection of two real branches of my curve. Refer local equation x is x squared minus y squared equal to 0. The second type is like this. It's so-called solitary double point, or sometimes they call elliptic. Oh, it's difficult to write here. Elliptic node. So what happens for such a double point? You can tell me that I wanted to consider only singularities which are transversal intersections of two branches of my curve. But such a point, such a solitary point, is in fact transversal intersection of two branches of my curve, but these branches are complex conjugate. Yeah, so the local equation is x squared plus y squared equal to 0. Well, I said that there are three types, and I described just two. So, it's a standard joke in this place that, you know, there are three types of mathematicians: those who know how to count and those who don't. So in fact, there is a third type, because remember that for me, a real curve is a complex curve, globally invariant and the evolution of complex conjugation. So I can have non-real double points. But in fact, I'm not interested in this non-real double points. And for the moment, I am not interested in hyperbolic ones. I am just interested in this solitary double point. I am interested in elliptic nodes. And so to understand the sign of my nodal rational curve, I just look at the number of solitary double points, number of elliptic nodes. And if this number is even, then the sign is plus. If this number is odd, then the sign is minus. Just to check that everybody is still with me. I understand that's complicated after lunch to follow. So what is the sign of this curve? So the sign is just -1 to S, where S is the number of solitary double points. And it's a very particular case of Virchow theorem. If you enumerate the curves in our collection with this Virchow sign, then the result does not depend on the choice of points, provided that points are in general position. So let me denote the configuration of points by omega. So omega is the configuration of my points. And now I cook such a number. Okay, so it's probably not a good idea to write here. So you will see nothing. Let me write this theorem here. So the number, I will introduce this notation inside the statement. So I'm accounting these curves with the Virchow signs. And the result I will denote in this way. So a priori, the result does depend on the collection of points. But I claim that this number does not. So the result of this signed enumeration does not depend on the choice of omega, of this configuration of 3D minus 1 points. And try to guess what is this number if D is equal to 3. It's in fact 8. So this is the value of the Virchow invariant, is W3. So I will drop this omega in the notation of the number because the result does not depend on the choice of omega. I will just write WD for the Virchow invariant. And so W3 is 8. And it's not the original proof by Harlamov, but in fact, the original proof is ideologically close to this one. So it gives you in particular this corollary that 8 is the minimal possible value for the number of real solutions in our enumerative problem. Because if I enumerate my curves with signs and I get 8, if I do the enumeration without signs, if I count each curve with a sign plus, then of course I cannot get a number which is smaller. Well, so what is, so before I switch to other enumerative problems, other examples of Virchow type invariants, so let me make 2 remarks. So the first one is that, remarks. The first one is is the following one. In this story, it's really important that we consider rational curves. In principle, one can generalize our enumerative problem. One can take more points. Let me try to use some color. So one can decide that instead of enumerating rational curves, passing some points, we can enumerate curves of given genus G. But in this case, we should add G to the number of points in our collection. So we can consider collections of 3D plus G minus 1 points in general position. And we can try to enumerate curves of degree D and of genus G, irreducible curves of genus G. And once again, in the complex situation, you will get an invariant. You will get a number that does not depend on the choice of particular choice of points, provided that points are in general position. And this number coincides with genus G Gromov-Fit invariant. But over the reals, you mean this number? Yes, a good question. All these Wilshire invariants are positive. And by the way, the first proof of this fact was tropical. So one can calculate these numbers in the tropical world. And once you decide to use Michalkin's correspondence theorem, and then you can play some combinatorial game in the tropical world, and you can prove that all these Wilshire invariants are positive.
Do they actually count some tropical curves?
Well, tropical curves are counted also with some multiplicities. So in fact, Michalkin's correspondence theorem tells you that if you want to, coming back to the genus G, because the statement is more general, so we can do it in any genus. So if you enumerate complex curves, if you work over the complex numbers, then Michalkin's correspondence theorem tells you that the number of curves you are interested in coincides with the number of tropical curves in the corresponding tropical enumerative problem, but tropical curves you should count with some multiplicities. And in fact, Michalkin's theorem is not a statement about an equality of numbers. It's a statement about certain bijection. And since it's a statement about bijection, you can enumerate real curves. And so in fact, you enumerate real curves close to the tropical limit. And if you're interested in the rational case in Wilshire invariant, so of course you can do this enumeration close to the tropical limit. So you count tropical curves with certain multiplicities, and you get the Wilshire invariants. So these Wilshire invariants are always positive. It's not true that all Wilshire invariants in more general situations are always positive, but in this enumerative problem, they are positive. Coming back to my first remark. So if you are interested in this more general enumerative problem, so if you want to enumerate curves of genus G, you can, of course, naively try to enumerate real curves. So still, all the solutions to our enumerative problem are nodal. You can try to enumerate real solutions with this Wilshire science, and the result, in general, is not an invariant. So this Wilshire enumeration does not give an invariant already starting from genus 1. So, and I don't know how to define this Wilshire type invariance in higher general, in P2. So, analogs of Wilshire invariance, of this Wilshire invariance, of Wilshire invariance of P2 for higher genus genera are not known. And the second remark, so since we already started to discuss it, so this Wilson-J invariance can be calculated in the tropical world. So one can calculate the corresponding Gromov-Witt invariance in the tropical world. One can calculate Wilson-J invariance, but surprisingly, one can do something more elaborated. So to express the corresponding Gromov-Witt invariance or the Wilson-J invariance in the tropical world, so once again we consider some tropical curves that are solutions to corresponding tropical enumerative problem, and these tropical curves are enumerated with certain multiplicities. So if you want to calculate the Gromov-Witt invariant, so there are so-called Mihalkin's multiplicities. If we want to get Wilson-J invariant, we should modify slightly the multiplicities. But in any case, these multiplicities are numbers. So to each tropical curve, we associate some number. But one can associate to a tropical curve a more sophisticated object. And this was a suggestion made by Florian Bloch and Lothar Goethe, something like 10 years ago. So they suggested to enumerate tropical curves appearing in these enumerative problems with polynomial multiplicities. So one can associate to each tropical curve a polynomial multiplicity. So a polynomial, it's a polynomial in one variable. That's a Laurent polynomial, symmetric Laurent polynomial in one variable. So one can associate to each tropical solution of the corresponding tropical enumerative problem the so-called Bloch-Goethe multiplicity. And this multiplicity is a Laurent polynomial, symmetric Laurent polynomial in one variable, and we will denote this variable Q. And it's once again, it's an easy combinatorial game in the tropical world. So we proved with Grisha Mikhalkin, also approximately 10 years ago, that if you do this enumeration in the tropical world using as multiplicities Bloch-Goethe multiplicities, then in the tropical world you get an invariant. So the result does not depend on the choice of points in the tropical projective plane. So you get some polynomial in one variable, symmetric Laurent polynomial as an answer. And so if you do this enumeration for rational curves in degree 3, so let me write down this polynomial for rational curves in degree 3. So we'll denote this polynomial B. So it depends on the degree, and it depends also on genus. So here the degree 3 and the genus is 0. And the answer like this. So I will not discuss the definition of Bloch-Goethe polynomials, but it's in fact it's an immediate consequence of the definition that I will not discuss. That when you plug Q equal to 1, you get the number of complex solutions. What is more surprising, it's a less direct consequence, but still a consequence of definition, that if you plug Q equal to -1, then you get the corresponding Wilson-J invariant. So you can think about these Bloch-Goethe polynomials as one parameter family interpolating between Gromov-Witten invariants and Wilson-J invariants. Yes?
So one question, I mean, Gromov-Witten invariants are defined through intersection theory in a moduli space. Is there a similar interpretation?
That's a very good question. So it's one of the main problems in real enumerative geometry that, of course, you can consider moduli spaces of objects you are interested in, but quite often, I would say typically, these moduli spaces are non-orientable. So it's quite complicated to do intersection theory in this moduli space. So Wilson-J invariants can be interpreted in this way, but you should cook your moduli space in really inappropriate ways. So in fact, you can look at some pieces and then glue these pieces in appropriate way to interpret this Wilson-J invariance, degree of some map or in some intersection theory terms. But when you do this gluing procedure, in fact, to show that the result is exactly what you need to get, in fact, you use the same arguments as in the proof of the Wilson-J theorem. So it's, in a sense, it doesn't give you an independent proof of the Wilson-J theorem. But of course, it's a very good question. So it's really probably the main problem in real enumerative geometry. Moduli spaces are typically non-orientable, so one should try to do something else. Yes?
So when you plug in Q, I think 1, you get the
Gromov-Witten invariant, yeah.
that suggests it is some kind of evaluation of the south of Hilbert scheme.
Well, so here everything, well, one can, this is another very good question, how to interpret these polynomials. So in my description, this polynomial, well, I didn't give a definition, but still I was speaking about some tropical enumeration. And in fact, what happens in this tropical enumeration, that if you enumerate tropical curves with Mihaltin's multiplicities, you get the number of complex solutions. But these Mihaltin multiplicities, they are presented as products. So you take a product over trivalent vertices of your tropical curve of some multiplicities of vertices. And each multiplicity of trivalent vertex is a positive integer number. What you do to obtain the Bloch-Goethe multiplicity of your curve, you just take the same product over trivalent vertices, but you replace the multiplicity of each trivalent vertex by Q analog of this multiplicity. And thus, by definition, when Q is equal to 1, you get back the multiplicity of your vertex. But in fact, conjecturally, these Bloch-Goethe polynomials are related to several other objects. And in particular, this is what is called Goethe-Schender conjecture. They're related to certain polynomials attached to certain relative Hilbert schemes. And if you think about these polynomials in these terms, so once again, it's more or less automatically by definition, the Q equal to 1 corresponds to the complex enumeration, but still it's really less clear why Q equal to -1 corresponds to the signed enumeration of real objects. But I claim that if we think about this Bloch-Goethe polynomials defined in the tropical world, then Q equal to -1 gives you, if you are in genus 0, it gives you Wilson-J invariant. If the genus is positive, then you get so-called tropical Wilson-J invariants. And it's not clear what are algebra geometric meanings of this tropical Wilson-J invariants. And it's still a widely open question. What is or what are reasonable algebra geometric interpretations of these Bloch-Goethe polynomials? So, for example, of coefficients of these polynomials, individual coefficients, of values at some other values of Q. So one can think about some, for example, other roots of unity or some other values to plug instead of Q, but it's completely unclear. There are several approaches. In fact, what I will discuss today is related to one of the approaches, so the approach proposed by Grisha-Mikhalkin, in order to understand this some algebraic nature of this Bloch-Guecci polynomials. Well, they are symmetric, in fact, just by definition. So these multiplicities, these Q analogs, are defined in such a way that each multiplicity this Q analog you use is symmetric. In fact, they're by definition symmetric, and in fact, by definition unimodular. So it grows and goes back. Okay, so let's now discuss another enumerative problem. So I will change now the setting. And okay, so let's write another enumerative problem. So still, I'd like to start with to enumerate rational curves, real rational curves. So we will be in the case of to start with the genus 0, and this was the case considered by Grisha-Mikhalkin. So the problem, the enumerative problem I'd like to consider is as follows. So now I will pick points in P2 of R in extremely non-general position. So this is my picture. This is my picture of P2 of R. So we have 3 axes of coordinates. I don't know. Well, some people, in fact, including me, prefer this picture. Sorry about that. Which of the pictures? Yeah, so that's what I'm saying. So not everybody prefers this picture. Okay, so by the way, looking at this picture, it's becomes more clear that we have 4 quadrants, right? And one of them I will call positive quadrant. And now I will choose my points on the boundary of this positive quadrant. So I will pick D points on the boundary, well, on this axis, on the boundary of positive quadrant. D points on the second axis. And, well, in principle, still, I will try to enumerate rational curves. So I should fix 3D minus 1 points. So, okay, let's follow this recipe. Let's fix 3D D minus 1 points on the third axis. Yeah, the total number of points is 3D minus 1. But in fact, this is independently on our choice and our preference between these 2 pictures. This is not very symmetric. Yeah, so it's not clear why this axis has this disadvantage not to be treated in the same way. But in fact, what happens? So if we decide to trace curves of degree D, rational, non rational, it doesn't mean. rationality is not important for the statement. So if we decide to trace through our 3D minus 1 points a curve of degree d, such a curve will have one extra point on this axis. Yeah, the total intersection should be d. And this extra point does not depend on the choice of the curve. So all curves of degree d passing through 3D minus 1 chosen point, they share one common extra point on the third axis. Just think about Viet theorem to prove this statement. Viet, it's a French mathematician. Well, it's if you want, what is Viet theorem? It's a theorem gives you an expression. So if you have a polynomial in one variable, you can express the coefficients of this polynomial in terms of the roots. Yeah? And so you can think about 3 polynomials in one variable corresponding to the axis. And this Viet theorem immediately tells you that the remaining root of this polynomial is determined by all the other roots. Well, this statement is a corollary of many other statements. So you can, the list of names you can add to the name of Viet is definitely longer than the list I could write on this blackboard. So let's now restore the. Let's fix d points also on the third axis. And my points are in this special Viet, sometimes called Menelaus position. So these points admit curves of degree d passing through all these points. But of course, my configuration should be generic among this Viet or Menelaus type configurations. Now, it would be reasonable to trace two curves of degree d through these points, but that's not what I'd like to do. I will trace real rational curves of degree 2d. Don't ask me why. I just want to. But of course, now I should somehow explain you what happens at these points, because now I have many other conditions to impose to have a finite collection of curves and under consideration. But in fact, now what I will ask my curves to do. So before I was asking the curves to pass through points. Now I ask each curve to be tangent to the axis of the corresponding point. And now the number of conditions is as it should be. Once again, we have a finite collection of curves satisfying these constraints. And I'd like to enumerate these curves with appropriate signs. So in fact, just a remark. So one should somehow treat carefully the case of the last point. And now, well, this is related to Thomas' talk yesterday. So now for the last point, this Viet theorem tells me that there are 2 possible positions for this last point. The position, so a given position and the symmetric one. Yeah, because now I should take the square root of something which is fixed. But I will consider an invariant of the same type as Thomas considered yesterday. So I will choose the particular position of this point. So my point is on, my extra point is also on the boundary of the positive quadrant. Well, now I should enumerate these curves with some signs. And okay, let's fix a sign. So now sign is determined by the parity of the number of elliptic nodes, of solitary nodes. But I will count only solitary nodes in the positive quadrant. So so if I take a real rational curve in this collection, so my real rational curve will have some one-dimensional part of the real locus, and it will have some number of solitary double points. And these solitary double points can in principle be everywhere, but I'm interested only in the number of solitary double points in the positive quadrant. And theorem proved by Grisha-Mikhalkin. The result of such enumeration is the invariant. You could ask me why Mikhalkin wanted to enumerate, to look only at solitary double points in the positive quadrant and not the total number of solitary double points. There are several possible answers to this question, but the most direct is that if you look at the parity of number of solitary double points everywhere, and you do the corresponding enumeration, then the result is not an invariant. Surprisingly, here it's important to enumerate only elliptic nodes, only solitary double points in the positive quadrant.
Search for something that is an invariant, not like you knew ahead of time that this has to be.
Well, in fact, it's easy to see that if you enumerate these curves, taking into account all the solitary double points, it's easy to see, it's easy to find the bifurcation which changes the number. But in fact, the true reason, well, it's already a true reason, but in fact, the reason for Mikhalkin to consider such enumeration, in fact, he was thinking about enumeration of real rational curves of degree D. And what I'm presenting here, I'm enumerating kind of squares of these curves. So I square the variables. And so from this perspective, it's really natural to consider solitary double points only in the positive quadrant. They correspond to solitary double points of initial curves of degree D. Well, and in fact, the theorem proved by Grisha is much more rich than what I wrote here. So in fact, one can do so-called refined enumeration of these curves. So one can introduce the notion of quantum index. So let me briefly discuss this notion. So to consider this quantum index of a real curve, I need to assume that, okay, let's discuss still curves, real curves in projective plane. So first of all, I need my curve to be separating. So what does it mean separating? What does it mean to be separating for a real curve? Okay, let's start with a Riemann surface equipped with an anti-holomorphic involution. So you have a Riemann surface. This is the most complicated Riemann surface I can draw. And this surface is equipped with an anti-holomorphic involution. So this involution has the fixed locus. And there are two possible situations. No, really two. Okay? So it can happen that this fixed locus divides our Riemann surface into halves exchanged by the complex conjugation. That's what I will call separating real curve. And it can happen that my real curve, my real Riemann surface, is non-separating, meaning that the fixed point set does not divide the Riemann surface. The complement is connected. So can you imagine such an involution on the torus? I'm sure you can. But just in case, let me draw another picture of my torus. And this is a fixed point set. Now I think you can imagine the involution. So both situations are of course possible, but I'm interested in this first case. I'm interested only in separating real curves. And the second condition, so we are discussing real curves in P2, so I'd like all intersection points with the coordinate axis I'd like all these intersection points to be real. Notice that all the curves appearing in this enumerative problem automatically satisfy the both restrictions. They're automatically separating a rational curve with non-empty real part is automatically separating, because we are speaking about a sphere with non-empty fixed locus of such an anti-holomorphic involution. So our curves are automatically separating. And I decided to choose to fix points on the axis, on the current axis. In fact, especially to make sure that all the intersection points with the axis are real. And so the statement proved by Grisha Mikhalkin. Okay, so probably I will change the blackboard. So if you consider such a real curve in P2, so a real curve satisfying these two constraints. Well, in fact, I explained what does it mean separating for Riemann surfaces, and we will have to deal with nodal curves. But if you have a nodal curve, for example, in P2, you look at the normalization of your curve, and then you apply this notion to the normalization. So I say that my nodal curve, my real nodal curve, is separating if the normalization is separating. So I have a separating real curve in P2. So the complex point set is C. So this is a complex point set of separating real curve. So one can look at the part of my curve in the complex torus. And my curve is separating, so I have two halves. C not plus one of C in this complex torus. Now I can look at the standard logarithmic map that gives you amoebas. And you can use this this map. Well, you can choose one of these halves. And then using this map, you can pull back the Euclidean area form, and you can integrate the result over a given half. And so each half gives a number. The result of this integration of the pullback of the Euclidean area form. And this number is of the form k p square. And Mihalkin's theorem tells you that k, provided that the separating real curve satisfies also the second condition. So with satisfying the second condition. All the intersection points with the axis are real. And then k is a half integer. In particular, if you deform your curve in such a way that your real curve remains separating and all the intersection points with the axis are still real, then you can't change this coefficient of p square. And this k is called the quantum index. Okay, is the quantum index so this theorem is proved by Mihalkin. And this is terminology introduced by Grisha. So it's quantum index of, in fact, this quantum index is attached not to the curve, but to a half of this curve. Because if you change the half, you change the sign of k. So this is quantum index of a given half of a curve. And now a more detailed statement of this Mihalkin theorem, and that, in fact, you can enumerate these curves for each value of quantum index separately. You can fix a given value of quantum index. You can consider halves of these real rational curves with given quantum index. You can enumerate them with the signs, and once again, you will get an invariant. So so for each value of quantum index, in this enumeration, one gets an invariant. So let me denote the result. So the result depends on the degree and the quantum index. And moreover, one can, let me write down it here. One can cook out the generating series of this invariance. So D is fixed, but the values of quantum index can change. So you can see this the sum over K of this invariance. You should renormalize this generating series a little bit. So the normalization is like this. And the claim and that the result is the Bloch-Goethe polynomial in this enumerative problem. So it's not the Bloch-Goethe polynomials I described before because our enumerative problem was different. But in this enumerative problem, you also have the corresponding Bloch-Goethe polynomial. And this is exactly what you get. In particular, notice that I'm saying something which is really difficult to believe. That's true. So you enumerate real solutions in this enumerative problem according to quantum indices. And just from this enumeration of real curves, you are able to recover the number of complex solutions. Because I enumerate real curves according to quantum indices, I cook this generating series, I divide by this normalization factor, and I plug Q equal to 1. This is the number of complex solutions. Okay, so I should finish. So let me just say that what we did with Zhenya Shustin, so we extended Mikhalkin's, well, at least some of Mikhalkin's statements to the case of genus 1 and 2 with joint work with Zhenya Shustin. And in fact, we even introduced 2 different enumerations. So enumerations with different signs of real solutions to the corresponding enumerative problems in genus 1 and 2. And a theorem that surprised me a lot. So a theorem we proved after introducing these 2 different ways of enumeration, that in fact, these 2 different ways of enumeration gives you up to some global sign the same invariance. In fact, it works also in Mikhalkin's case, also in genus 0. So in fact, one can extend this Mikhalkin's enumeration to genera 1 and 2, even in 2 different ways. But these 2 different ways provide the same collection of invariants up to some global sign that depends only on the degree. Thank you.